Look up at the night sky, and you'll see countless stars shimmering like distant lanterns. But have you ever wondered where they come from? Hidden in the depths of space, far beyond what our eyes can see, lies a cosmic workshop where stars are born. Picture vast, swirling clouds of dust and gas drifting silently through the darkness. These interstellar clouds are more than just ghostly wisps in the void. They're the universe's most prolific nurseries, crafting the very stars that light up galaxies. And today, we're going to pull back the curtain on these mysterious structures, revealing how they shape the cosmos in ways that will leave you in awe. Think of these clouds as the raw materials of creation. Over millions of years, gravity works its magic, pulling together particles so tiny they'd vanish in a beam of sunlight. Yet from these minuscule beginnings, immense forces awaken. A single cloud can collapse under its own weight, igniting the birth of not just one star, but hundreds, even thousands. The process is delicate, chaotic, and breathtakingly beautiful, like watching a cosmic ballet where dust and gas pirouette into fiery new suns. And here's the most astonishing part. Without these interstellar clouds, our universe would be a dark, empty place. No stars, no planets, no life as we know it. This journey will take us from the smallest grains of cosmic dust to the grandest structures in the universe. We'll explore how these clouds evolve, how they sculpt entire galaxies, and even how they hold clues to our own origins. Because every atom in your body, every breath you take, was once part of this star-forming chaos. So buckle up as we venture into the heart of these celestial cradles, uncovering the secrets of how darkness gives way to light, and how emptiness transforms into the dazzling tapestry of the cosmos. The story of interstellar clouds isn't just about distant space, it's about the very fabric of existence itself. These interstellar clouds, these cosmic cradles of creation, are far more than just hazy patches in the night sky. They're dynamic, ever-changing structures where the universe quietly weaves its magic. Picture them as vast reservoirs of potential, each wisp of gas, each speck of dust carrying the ingredients needed to build stars, planets, and the very chemistry of life. Hydrogen dominates these clouds, left over from the birth of the universe itself, mingling with helium and traces of heavier elements forged in the hearts of long-dead stars. It's a cosmic recycling program on the grandest scale, where the ashes of ancient supernovae become the building blocks of new worlds. Some of these clouds are so thin, so ethereal, that a single particle might drift for miles before encountering another. Others are so dense they blot out the light of stars behind them, appearing as inky voids against the glittering backdrop of the Milky Way. The famous Horsehead Nebula, for instance, is a dark silhouette carved by stellar winds, while the Orion Nebula glows with the energy of newborn stars. These differences in density aren't random. They're the result of gravity's subtle tug, magnetic fields threading through space, and the shock waves from distant stellar explosions. Over time, these forces sculpt the clouds into intricate shapes, preparing them for their ultimate transformation. And here's what's truly fascinating. Within these clouds, chemistry thrives. Simple molecules like carbon monoxide and water ice cling to dust grains, while more complex organic compounds form in the cold, dark depths. These ingredients don't just make stars, they're the precursors to planets, comets, and even the molecules that would one day spark life. Every time you take a breath, you're inhaling atoms that once floated in one of these clouds billions of years ago. So when we study these celestial nurseries, we're not just uncovering the birth of stars, we're tracing our own cosmic ancestry, one molecule at a time. The transformation from a cold, lifeless cloud to a blazing star begins with something almost imperceptible, a slight unevenness in the density of gas and dust. In the vast quiet of an interstellar cloud, gravity is always at work, tugging ever so gently on every particle. Wherever a random clump forms, even one slightly denser than its surroundings, gravity seizes the opportunity. It pulls more material inward, growing heavier and more compact with each passing eon. At first, the collapse is slow, almost hesitant, like the first drops of rain before a storm. But as the clump grows denser, gravity's grip tightens, accelerating the process until the heart of the cloud becomes a swirling, chaotic maelstrom. Within this collapsing core, something extraordinary happens. As gas and dust pile inward, friction and pressure begin to heat the material. At first, it's just a faint warmth, barely noticeable against the cold of space. But as the compression intensifies, temperatures climb first to hundreds, then thousands of degrees. The dust grains vaporize, and atoms collide with such force that electrons are torn away, creating a seething plasma. Deep in the center, where pressures become unimaginably intense, hydrogen atoms are forced so close together that they overcome their natural repulsion and fuse. In that instant, nuclear fire ignites and a star is born. But what sparks this chain reaction in the first place? Sometimes it's the shockwave from a nearby supernova, rippling through the cloud like a stone tossed into a pond. Other times, it's the subtle push of starlight from a distant giant, nudging gas just enough to upset the delicate balance. Even the random churn of turbulence within the cloud itself can create the right conditions. Once begun, though, the process takes on a life of its own. The newborn star begins to carve out its space, its radiation and winds pushing back against the remaining cloud, shaping it into glowing filaments and cavities. And here's the remarkable part: no two stellar births are exactly alike. A dense, massive cloud might forge a brilliant blue giant, burning furiously and dying young. A smaller, quieter collapse could create a modest yellow sun like our own, stable for billions of years. Some stars form in near isolation, while others emerge in clusters, siblings bound together by their shared origin. Yet all of them, from the mightiest to the humblest, begin the same way with nothing more than dust, gravity, and time. While the gas in interstellar clouds provides the bulk of the raw material for stars, it's the dust, those tiny, unassuming grains, that holds the real secrets to how star formation unfolds. Imagine these microscopic particles as cosmic architects, silently shaping the destiny of entire stellar nurseries. Each speck, no larger than a fraction of a human hair, is made of heavier elements like silicon, carbon, and iron, remnants of ancient stars that lived and died long before our sun even existed. These dust grains may seem insignificant, but their role is anything but. Floating within the clouds, they act like miniature shields, absorbing and scattering the intense radiation from nearby stars. This creates pockets of shadow where gas can cool and condense without being torn apart by external energy. It's a bit like a cosmic umbrella, sheltering the delicate process of collapse until gravity can take firm hold. Without this protective effect, many star-forming regions would remain too turbulent, their gas too agitated to ever coalesce into new suns. But dust doesn't just block light, it also kickstarts chemistry on a molecular level. On the frigid surfaces of these grains, atoms meet and stick, forming simple molecules like hydrogen and carbon monoxide. Over time, these reactions grow more complex, giving rise to water ice and even organic compounds. Think of each dust particle as a microscopic laboratory where the building blocks of future planets and perhaps life itself first take shape. some of the molecules clinging to these grains today might one day end up in the atmosphere of a distant world or the cells of an unknown organism. The relationship between gas and dust is a delicate balancing act. Too much dust and a cloud becomes opaque, trapping heat that can stall collapse. Too little, and radiation strips away the gas before stars can form. It's this precise interplay that determines whether a cloud gives birth to a single star or a glittering cluster, whether it creates a stable solar system like ours or a chaotic realm of scattered worlds. And here's the remarkable twist. The dust we're talking about isn't just some distant curiosity. Every time you see sunlight filtering through a window, those dancing motes in the beam are distant cousins to the cosmic dust that helped build our own solar system. The iron in your blood, the silicon in your bones, all of it once floated in these vast dark clouds, waiting for gravity to weave it into something new. So when we study these tiny grains, we're not just uncovering how stars are born, we're tracing the path that led to us. Deep within those swirling interstellar clouds, where dust and gas seem to drift at random, there's an invisible hand guiding the chaos magnetic fields. These aren't the simple magnets you stick to your fridge. They're vast dynamic forces woven through the fabric of space itself, stretching across light years with the power to shape the birth of stars. Picture them like cosmic puppet strings, subtly directing where gas flows, how quickly it collapses, and even the spin of newborn stars. Without these fields, the universe's stellar nurseries would look utterly different, and the stars they produce might never form planets like ours. At first glance, it's hard to imagine something as intangible as magnetism playing such a crucial role in star formation. But think of it this way. When a cloud begins to collapse, the gas doesn't just fall straight inward like water down a drain. Charged particles, ions and electrons get caught in the magnetic field lines, spiraling along them like beads on a wire. This creates resistance, slowing the collapse in some regions while funneling material into others. It's why some parts of a cloud fragment into dense knots ripe for star formation, while others remain diffuse and quiet. The influence doesn't stop there. As a protostar takes shape, its rotation speeds up, much like a figure skater pulling in their arms. Left unchecked, this spin would tear the young star apart before it could fully form. But magnetic fields act as a cosmic brake, transferring angular momentum outward into the surrounding disk. This not only stabilizes the star, but also shapes the architecture of any future planetary system. The planets in our solar system, for instance, owe their orderly orbits in part to these ancient magnetic forces. Yet mysteries remain. How do these fields originate in the first place? Some likely stem from the turbulent motions of ionized gas within the clouds themselves, while others might be relics from earlier stellar explosions, or even the primordial magnetic fields woven into the universe since its infancy. And their strength varies wildly. Some clouds have fields so weak they're barely detectable, while others are so strong they dominate every aspect of star birth. What's truly astonishing is how these invisible forces leave their mark long after a star ignites. The orientation of a star's magnetic field can influence the eruptions on its surface, the winds it blows into space, and even the habitability of its planets. So the next time you gaze at the night sky, remember, those twinkling lights aren't just products of gravity and gas. They're the children of a hidden magnetic symphony playing silently in the darkness of space. Far from the serene, drifting clouds we imagine, stellar nurseries are some of the most violent places in the universe's cosmic war zones where creation and destruction wage an endless battle. Picture a newborn star, barely ignited, already blasting its surroundings with radiation so intense it strips electrons from atoms and shreds nearby gas clouds. These young stellar giants don't just glow, they roar, hurling out supersonic winds that carve vast cavities in their birthplaces. Meanwhile, the most massive stars burn fast and die young, exploding as supernova that send shockwaves rippling through the nursery, scattering material in all directions. This chaos isn't just random destruction, it's a vital part of the star-making process. When a supernova's shockwave slams into a nearby gas cloud, it can compress the material, triggering a new wave of star formation like a domino effect. The Orion Nebula, one of our closest stellar nurseries, is a perfect example. Its brilliant core, illuminated by the trapezium stars, is simultaneously giving birth to new suns while being torn apart by their fierce radiation. Some pockets of gas collapse under the pressure, while others are blown away entirely, their potential stars snuffed out before they can ignite. But the violence doesn't stop there. Stellar winds, streams of charged particles racing outward at millions of miles per hour, sculpt the surrounding nebula into bizarre shapes, from towering pillars to delicate filaments. The iconic pillars of creation in the Eagle Nebula, immortalized by Hubble, are being eroded by these very forces, their surfaces glowing as they evaporate under the onslaught. Yet, even as they dissolve, the densest knots within them may be collapsing into new stars hidden from view. It's a breathtaking paradox. The same forces that destroy also create, ensuring the cycle of star birth continues. And here's the twist. This turbulence actually regulates a galaxy's star-forming efficiency. Too much violence and gas is blown away before it can form stars. Too little and the galaxy stagnates, its material locked in dormant clouds. The Milky Way strikes a delicate balance, with just enough chaos to keep star birth steady, but not so much that it exhausts its fuel too quickly. Other galaxies aren't so lucky. Some, like those in dense galaxy clusters, have their gas ripped away entirely, leaving them barren and starved. What's truly humbling is realizing that our own solar system was likely shaped by these forces. The shockwave from a nearby supernova may have triggered the collapse of the cloud that became our sun, while stellar winds from massive neighbors could have influenced the composition of our early planet-forming disk. The violence of stellar nurseries isn't just a spectacle, it's the forge where the fate of worlds is decided. Among the countless stars lighting up our galaxy, some travel in tight-knit family stellar clusters bound together by their shared birthplace. These clusters are cosmic time capsules, holding clues about how stars emerge from the same swirling cloud yet take on such different fates. Picture a vast interstellar cloud collapsing, not into a single star, but fragmenting into dozens or even thousands of protostars simultaneously. The result is a glittering swarm, a temporary gathering where sibling stars shine side by side before gravity and motion eventually pull them apart. What determines whether a cloud gives rise to a modest cluster of a few stars or a dazzling metropolis like the Orion Nebula's trapezium cluster, home to thousands? It all comes down to the cloud's original blueprint: its mass, how tightly packed its gas is, and the level of turbulence churning within it. A massive, dense cloud with violent internal motions has the raw material and energy to spawn a rich cluster, while a quieter, more diffuse one might produce only a loose handful of stars. It's like comparing a bustling city to a rural village. Both are communities, but their scale and structure depend entirely on the resources and conditions at their founding. But clusters don't stay intact forever. Over hundreds of millions of years, gravitational tugs from passing gas clouds, spiral arms of the galaxy, and even individual stars gradually loosen their bonds. Stars begin drifting away like leaves scattered by the wind, until the cluster's identity fades into the background of the Milky Way. Our own sun likely began its life in such a cluster, its siblings now lost among the galaxy's 100 billion stars. Yet traces of their shared origin might still linger, chemical fingerprints in their atmospheres or similar trajectories through space, waiting for sharp-eyed astronomers to piece the family back together. The most fascinating part, studying these clusters lets us rewind the cosmic clock. By observing young clusters still embedded in their birth clouds, like the fiery jewels of the Carina Nebula, we see star formation in action. Meanwhile, ancient globular clusters, dense, spherical swarms orbiting the galaxy's outskirts, offer snapshots of the universe's early days, their stars nearly as old as the Milky Way itself. Each type tells a different chapter of the story, revealing how conditions in interstellar clouds have shaped the galaxy's stellar population over billions of years. And here's the kicker: these clusters don't just teach us about stars. Their survival or dissolution influences where planets form, how heavy elements spread, and even where life might find a foothold. A star born in a dense cluster faces harsh radiation from neighbors, potentially stripping away fledgling atmospheres, while one in a quieter setting has a calmer environment for planets to grow. So when we unravel the puzzle of star clusters, we're not just exploring stellar origins, we're mapping the pathways that led to worlds like ours. Not every collapsing cloud in the universe gets to bask in the glory of stellar stardom. For some, the journey ends in cosmic ambiguity, objects caught between worlds, too substantial to be planets yet too feeble to ignite as true stars. These are brown dwarfs, the shadowy underdogs of star formation, glowing dimly with nothing but the fading embers of their birth heat. Imagine a celestial object so unassuming it doesn't even qualify for the main stage of stellar evolution, yet its very existence helps us unravel the fine line between what makes a star and what makes a planet. Round dwarfs begin their lives much like their brighter siblings, born from the same swirling clouds of gas and dust, but somewhere along the way their collapse stalls. Perhaps the initial fragment was too small or the cloud too sparse, leaving the budding object without enough mass to muster the crushing pressures needed for hydrogen fusion, the defining engine of a true star. The result is a cosmic halfway house, an object with a mass ranging from about 13 times that of Jupiter up to roughly 8% of our Sun's mass. Too light to shine brightly, yet too heavy to be a mere planet, these objects simmer in the darkness, emitting only a dull infrared glow as they slowly cool over billions of years. What makes them fascinating isn't just their failure to shine, but the secrets they hold about the extremes of star formation. Brown dwarfs challenge our definitions, blurring the lines between categories. Some even possess swirling storms and bands of clouds like Jupiter, while others may have thin, fleeting atmospheres rich in molecules like methane and water vapor. A few have been found orbiting true stars, while others drift alone through interstellar space, ghostly remnants of a process that almost was. Their dim glow makes them hard to spot, but modern telescopes have peeled back the veil on these elusive objects. The more we find, the more we realize how common they might be, lurking in the shadows of nearly every stellar nursery, a silent population of cosmic almost stars. Some researchers speculate that there could be as many brown dwarfs as there are regular stars in our galaxy, a hidden multitude rewriting our understanding of how interstellar clouds distribute their material. And here's the kicker: studying these failed stars doesn't just teach us about star formation's lower limits. It also offers a window into the atmospheres of gas giants beyond our solar system. Brown dwarfs share traits with both stars and planets, making them ideal laboratories for understanding how weather, chemistry, and heat flow operate in environments unlike anything we see nearby. So while they may not shine brightly, their dim light illuminates some of the most intriguing questions in astrophysics. Where does a star end and a planet begin? And what other cosmic in-betweeners are waiting to be discovered in the depths of space? Perhaps the most poetic twist is that brown dwarfs, though failed by stellar standards, might still host worlds of their own. Some theories suggest these objects could have orbiting planets, dim, frigid realms where the sun never truly rises. If life exists in such places, it would thrive under an eternal twilight, warmed only by the faint infrared glow of a brown dwarf. It's a hauntingly beautiful thought. Even in their quiet obscurity, these cosmic misfits might still cradle the possibility of something extraordinary. Interstellar clouds might seem like simple collections of gas and dust, but hidden within their icy hearts lies an astonishing chemical tapestry, one that could hold the key to life itself. In the freezing void of space, where temperatures hover just a few degrees above absolute zero, atoms and molecules engage in a slow-motion dance, bonding in ways that defy expectations. Water ice coats microscopic dust grains, ammonia lingers in the frigid darkness, and even complex organic molecules like methanol and formaldehyde emerge from the chaos. These aren't just random reactions, they're the universe's first steps toward building the ingredients for planets, oceans, and perhaps even biology. The chemistry of these cosmic clouds begins with something deceptively simple: cold. On Earth, we think of heat as the driver of chemical reactions, but in the depths of space, the opposite is true. Extreme cold slows atoms down, allowing them to linger just long enough on the surface of dust grains to form fragile bonds. Hydrogen, the most abundant element, teams up with oxygen to create water ice, with nitrogen to form ammonia, and with carbon to spawn methane. Over millennia, these basic molecules grow more elaborate, assembling into chains and rings that resemble the precursors of life's building blocks. Some of the most complex molecules ever detected in space, like ethyl alcohol and even the sugar glycolaldehyde, have been found lurking in these stellar nurseries. What's truly remarkable is how these cosmic ingredients might have hitchhiked their way to Earth. When our solar system was just a collapsing cloud of gas and dust, it likely inherited these pre-made molecules from the larger interstellar cloud that birthed it. Comets and asteroids formed from that same primordial material could have later delivered them to our young planet. Picture this: the water in your glass, the nitrogen in your DNA, even the carbon in your cells might have once been part of a vast, frozen molecular reservoir drifting between the stars. Yet the story doesn't end there. These chemical factories also shape how stars and planets form. Water ice, for instance, acts like cosmic glue, helping dust grains stick together to form larger particles, the first steps toward planetesimals and eventually worlds. Organic molecules trapped in comets could have jump-started the chemistry of life on countless planets. Even the ratio of different isotopes in these clouds leaves a fingerprint, allowing astronomers to trace which stellar nurseries contributed material to our solar system. And here's the most tantalizing possibility: some of these molecules might be direct precursors to life. The discovery of amino acids in meteorites suggests that the basic components of proteins were already present in space long before Earth existed. Could the same processes happening right now in distant clouds be seeding other worlds with life's raw materials? Every new molecule detected in these cosmic cauldrons brings us closer to answering that profound question. So when we peer into the chemistry of interstellar clouds, we're not just studying distant space, we're uncovering the recipe for existence itself. Interstellar clouds are more than just star factories. They're the master architects of galaxies, silently shaping the grand structures we see across the cosmos. Picture a spiral galaxy like our Milky Way, its arms swirling with stars and glowing gas. Those elegant curves aren't just random decorations. They're the result of immense molecular clouds, their gravitational pull helping to sculpt and maintain the galaxy's spiral pattern. Like invisible hands molding clay, these clouds channel the flow of gas, stars, and energy, creating the dynamic beauty we admire from afar. But their influence runs even deeper. When massive stars explode as supernovae, they blast heavy elements forged in their cores back into the surrounding clouds. This enriched material becomes the raw ingredient for the next generation of stars and their planets. Over billions of years, this cycle of creation, destruction, and rebirth transforms a galaxy's chemistry, seeding it with the carbon, oxygen, and iron needed for rocky worlds and ultimately life. Our own solar system is a product of this cosmic recycling program, built from the ashes of countless ancient stars that once lived and died in these sprawling clouds. Some clouds play an even more dramatic role, funneling gas toward the supermassive black holes lurking at galactic centers. As these behemoths feast on infalling material, they unleash titanic energies that can heat surrounding gas, trigger star formation, or even suppress it entirely. The balance between creation and destruction in these regions determines whether a galaxy becomes a bustling stellar metropolis or a quiet backwater. In extreme cases, the interplay between clouds and black holes can launch jets of matter thousands of light years into space, shaping the galaxy's fate for eons. Yet the story doesn't end there. Dwarf galaxies, the smallest and most pristine in the universe, offer a glimpse into how these processes began. Their interstellar clouds, less polluted by generations of stars, mimic conditions in the early cosmos. Studying them reveals how the first galaxies pulled together their meager gas reserves to spark their earliest stars that would later flood the universe with the first heavy elements. What's truly humbling is realizing that the same forces shaping galaxies billions of light years away also sculpted our own cosmic neighborhood. The position of our sun, the composition of our planets, even the atoms in our bodies, all of it traces back to the delicate dance between interstellar clouds and the galaxies they build. So when we gaze at the night sky, we're not just seeing stars, we're witnessing the legacy of these invisible architects whose silent work continues to shape the universe around us. Peering into the heart of an interstellar cloud isn't as simple as pointing a telescope at the night sky. These cosmic nurseries cloak their secrets in layers of dust and gas, forcing astronomers to become cosmic detectives, assembling clues across the entire spectrum of light. Imagine trying to study a snowstorm by only looking at the flakes. You'd miss the wind, the temperature shifts, the way the storm interacts with the landscape. That's why observatories around the world and in space work in concert, each instrument revealing a different piece of the puzzle. Radio telescopes, with their massive dish antennas, are particularly adept at mapping the coldest, darkest corners of molecular cloud. They detect the faint whispers of carbon monoxide and other molecules tumbling through space, tracing structures invisible to optical telescopes. The Atacama Large Millimeter Array in Chile, for instance, stitches together signals from 66 radio antennas to create staggeringly detailed maps of star-forming regions. Meanwhile, infrared telescopes like the James Webb Space Telescope act as cosmic night vision goggles, piercing through thick dust to spot newborn stars still wrapped in their dusty cocoons. These glowing embers, hidden from visible light, radiate warmth that infrared sensors can capture in exquisite detail. But the story doesn't stop there. X-ray observatories like Chandra reveal the violent side of stellar nurseries, the searing million-degree winds from massive stars and the shockwaves of supernova remnants slamming into surrounding gas. Ultraviolet telescopes, on the other hand, catch the harsh glare of young, hot stars as they ionize their birth clouds, carving out vast cavities. Even gravity itself has become a tool, with observatories like LIGO detecting ripples from distant neutron star collisions that may have seeded nearby clouds with heavy elements. The real breakthrough comes when these perspectives merge, like combining black and white film, color photos, and thermal imaging of the same scene. Multi-wavelength observations reveal dimensions no single instrument could capture alone. A dark nebula that appears as a mere shadow in visible light might glow brightly in radio waves, while its newborn stars blaze in infrared and X-rays. This symphony of data lets researchers reconstruct the full life cycle of interstellar clouds, from their quiet beginnings to their explosive transformations. What's astonishing is how rapidly these tools are evolving. Next-generation telescopes will map the magnetic fields threading through clouds in 3D, while advanced spectrometers analyze the chemical fingerprints of molecules light years away. Some projects even aim to catch star formation in real time, observing changes over months rather than millennia. Every technological leap peels back another layer of the mystery, showing us not just how stars are born, but how their birth shapes everything that follows. And here's the beautiful part: these observations aren't just about distant clouds. They're mirrors reflecting our own origins. The processes we witness in Orion or the Carina Nebula are echoes of the same forces that crafted our solar system 4.5 billion years ago. So when astronomers train their telescopes on these cosmic nurseries, they're not just exploring space, they're reading the story of where we came from, written in the language of light. Interstellar clouds might seem timeless, hanging in the void like unchanging sculptures, but they're anything but permanent. These cosmic structures are constantly in motion, caught in a slow-motion dance of creation and destruction that spans millions, sometimes billions of years. Their life cycle begins in the faintest wisps of gas, drifting through the galaxy's spiral arms. These tenuous threads, stirred by stellar winds or supernova shockwaves, gradually gather mass, clumping together under gravity's patient pull. Over eons, what starts as a diffuse haze becomes a dense, bustling stellar nursery, teeming with the raw materials for new stars. Yet not every cloud gets the chance to shine. Some meet a violent end, ripped apart by the very stars they helped create. Massive stars, blazing with intense radiation, act like cosmic sandblasters, eroding their birth clouds from within. Their ultraviolet light ionizes surrounding gas, carving out vast cavities and leaving behind glowing shells of plasma. Supernovae deliver even more dramatic blows, their shockwaves shredding nearby clouds into filaments and knots. It's a paradox of nature. The same forces that give birth to stars also dismantle the clouds that nurtured them. But here's where the story takes a fascinating turn. Destruction in space isn't an ending, it's a transformation. The material blown away by stellar winds and explosions doesn't vanish. It disperses into the interstellar medium, mingling with other gas and dust. Over time, gravity gathers these scattered remnants anew, weaving them into fresh clouds that will one day collapse into another generation of stars. This recycling process is the universe's ultimate sustainability program, where every atom gets countless chances to be part of something new. The Milky Way itself is a testament to this cycle. Our galaxy's spiral arms, those majestic swirls of light, are essentially conveyor belts of star formation regions where denser gas accumulates, sparks new stars, and then dissipates, only to regroup elsewhere. The Sun, Earth, and everything on our planet are products of this grand recycling scheme, built from elements forged in long-dead stars and scattered across space by ancient supernovae. Without the continual death and rebirth of interstellar clouds, galaxies would exhaust their star-forming fuel, leaving the universe dark and sterile. What's truly remarkable is how much this life cycle varies. Some clouds, like those in the Orion Nebula, are bustling stellar factories, collapsing rapidly under their own weight. Others, like the dark, cold Bok globules, resist collapse for eons, hovering on the edge of stability. A few might even escape star formation entirely, drifting until they're torn apart by galactic tides or collisions with other clouds. Each path tells a different story about the conditions in our galaxy, its turbulence, its chemistry, even its history of violent stellar deaths. And here's the profound implication. By studying these clouds, we're not just mapping where stars are born today. We're piecing together the Milky Way's autobiography, written in gas and dust. The composition of a cloud reveals which generations of stars contributed to it, while its shape and motion hint at the forces that shaped it. In tracing their evolution, we uncover clues about how galaxies grow, change, and ultimately fuel the endless cycle of stellar birth and rebirth. So the next time you gaze at a nebula, remember, you're witnessing a single frame in a cosmic epic that's been unfolding for billions of years, with countless chapters yet to come. Among the vast tapestry of interstellar clouds, giant molecular clouds stand as the true titan structures so immense they could swallow entire star systems without a trace. Picture a cosmic archipelago stretching over hundreds of light years, each dense knot within it holding the potential to ignite thousands of new suns. These are not just larger versions of ordinary clouds. They're galactic-scale engines where gravity and turbulence collide on a staggering scale, forging stars in numbers that defy imagination. Take the Tarantula Nebula in the Large Magellanic Cloud, for instance. This colossal stellar factory churns out stars at a frenzied pace, its glowing tendrils illuminated by clusters of massive young stars. Or consider the Rho-Ophiuchi Cloud Complex, a sprawling nursery just 400 light-years from Earth, where dark lanes of dust weave through glowing gas like cosmic brushstrokes. These clouds don't just form stars, they birth entire stellar communities, with sibling stars bound together by their shared origin before slowly drifting apart over eons. What makes these giants so extraordinary isn't just their size, but their intricate internal machinery. Within them, gravity works in concert with supersonic turbulence, creating a fractal landscape of filaments, knots, and voids. Some regions collapse rapidly under their own weight, spawning massive stars that blaze to life in just a few 100,000 years. Others simmer slowly, producing smaller stars like our Sun over millions of years. The interplay between these processes determines whether a cloud becomes a fireworks display of brilliant, short-lived stars or a steady producer of stable, long-lasting suns. Yet these clouds are more than just star factories, they're galactic architects. Their sheer mass shapes the structure of spiral arms, their gravitational pull helping to maintain the grand design of galaxies like our own. When massive stars within them explode as supernovae, the shock waves ripple through the surrounding cloud, triggering new rounds of star formation while seeding the galaxy with heavy elements. It's a self-perpetuating cycle. Stars are born from the cloud, enrich it with new materials, and die in explosions that birth the next generation. The most fascinating aspect might be their ephemeral nature. Despite their staggering scale, giant molecular clouds are fleeting by cosmic standards, lasting only 10 to 30 million years before radiation and stellar winds tear them apart. In that brief window, they transform vast reservoirs of cold gas into the blazing stars that light up galaxies, proof that even the mightiest structures in the universe are just temporary waypoints in an endless cycle of creation and renewal. Deep in the heart of a collapsing interstellar cloud where gravity's grip grows stronger by the second, a new cosmic chapter begins, the birth of a protostar. This isn't yet a true star, but a dense, hot core gathering mass like a celestial snowball rolling downhill. Imagine a swirling vortex of gas and dust, so thick it blots out all light, yet pulsing with the energy of something struggling to be born. At its center, temperatures soar as particles collide with increasing violence, but true nuclear fusion, the hallmark of a star, still lies just out of reach. Surrounding this embryonic sun, something equally extraordinary takes shape. A vast, spinning disk of material stretching billions of miles across. Picture a cosmic carousel, with gas and dust whirling so fast that centrifugal force flattens it into a thin, pancake-like structure. This protoplanetary disk is far from chaotic. It's a meticulously organized construction zone, where the smallest grains of dust begin sticking together, forming the first building blocks of planets. Within these disks, the universe lays the groundwork for solar systems like ours, one microscopic collision at a time. The diversity of these disks is staggering. Some, like the one that birthed our solar system, are relatively orderly, with clear gaps where young planets have already begun carving out their orbits. Others, like the disk around the young star HL Tau, resemble a cosmic dartboard, with concentric rings of material separated by stark voids, evidence of planets forming in real time. Then there are the outliers, like those around binary stars, where disks warp into bizarre shapes under the tug of two competing gravitational forces. Each configuration tells a different story about how planetary systems emerge from the chaos. What's truly astonishing is the speed at which these disks evolve. In just a few million years, a blink in cosmic terms, dust grains no larger than smoke particles can grow into kilometer-wide planetesimals, then into full-fledged worlds. The process isn't gentle. Collisions between growing bodies send shockwaves through the disk, while the young star's radiation blows away lighter gases, leaving behind rocky cores and gas giants in its wake. Some planets migrate inward, swallowed by their star, while others are flung into the cold depths of interstellar space. It's a cosmic survival game, with only the most strategically placed worlds enduring to maturity. Yet these disks aren't just construction sites, they are also chemical laboratories. Near the protostar, temperatures are so high that silicates and metals vaporize, only to recondense into new mineral forms farther out. Water ice freezes into solid grains beyond the snow line, while complex organic molecules assemble in the colder outskirts. These gradients explain why our solar system has rocky inner planets and gaseous outer ones, why asteroids differ from comets, and perhaps even why Earth ended up with the perfect ingredients for life. Modern telescopes have given us front-row seats to this celestial drama. The Atacama Large Millimeter Array has captured razor-sharp images of disks with intricate spiral arms, likely sculpted by hidden planets. The James Webb Space Telescope peers through dust to spot water vapor and carbon-rich compounds swirling around infant stars. Even more thrilling are the occasional surprises, like disks with bizarre asymmetries, or ones where planets seem to form much faster than theory predicts. Each discovery peels back another layer of mystery, revealing how common or how rare systems like ours might be across the cosmos. The most profound realization. Protoplanetary disks are more than just planetary factories. They're time capsules, preserving the conditions of their birth while simultaneously shaping the futures of their stellar systems. Every asteroid, every comet, every planet in our solar system carries chemical fingerprints tracing back to that primordial disk. And somewhere out there right now, another disk is quietly assembling worlds of its own, some perhaps destined to nurture life as extraordinary as our own. When a massive star reaches the end of its life, it doesn't fade quietly into the cosmic background. It goes out with a cataclysmic bang that echoes across the galaxy. A supernova explosion unleashes more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime, sending shockwaves rippling through space at millions of miles per hour. These aren't just spectacular light shows, they're cosmic sculptors, reshaping interstellar clouds with the brute force of a stellar sledgehammer. Picture the aftermath of such an explosion. The shockwave slams into nearby gas clouds like a tsunami, compressing them so violently that pockets of gas collapse under the pressure. In some cases, this triggers a chain reaction. Dense knots form within the cloud, gravity takes over, and suddenly, a wave of new star birth begins. The Orion Nebula, one of the most active stellar nurseries visible from Earth, might owe its bustling activity to shockwaves from ancient supernovae that jump-started star formation like a cosmic domino effect. But supernovae don't just create, they also destroy. The same shockwave that compresses gas in one region can tear apart delicate structures in another, shredding nearby clouds before they have a chance to form stars. The pillars of creation in the Eagle Nebula, for example, are slowly being eroded by radiation and stellar winds from nearby massive stars, stars that will one day explode as supernova, finishing the demolition job. It's a delicate balance. Too much force and a cloud is blown apart, just enough, and it collapses into a new generation of stars. The most profound legacy of supernova, though, lies in what they leave behind. As the dying star explodes, it hurls newly forged heavy elements, carbon, oxygen, iron, even gold, into the surrounding space. These atoms, cooked in the star's fiery core, become part of the interstellar medium, enriching future clouds with the building blocks of planets and life. Every iron atom in your blood, every calcium atom in your bones, was once blasted into space by a supernova billions of years ago. We can still see the ghosts of these explosions today. The Crab Nebula, a tangled web of glowing filaments, is the remnant of a supernova observed on Earth in the year 1054. Its expanding shell of gas, visible even in amateur telescopes, continues to race outward at over 3 million miles per hour. Similar remnants dot our galaxy, each one a testament to the explosive death of a massive star and the rebirth it sparked in its wake. Supernova remind us that destruction and creation are two sides of the same cosmic coin. Without these violent explosions, galaxies would lack the heavy elements needed for rocky planets, and star formation might stagnate without the shockwaves to compress gas. They're the ultimate recyclers, ensuring that the death of one star becomes the birth of many others, a cycle as old as the universe itself. Among the glowing tapestries of nebulae that adorn our galaxy, some patches of space refuse to shine, dark nebulae, the universe's shadow puppets. These Inkai voids aren't empty, they're dense fortresses of dust, so thick they swallow starlight whole. The Horsehead Nebula is one of the most famous, its silhouette rearing against the glowing gas of Orion like a cosmic chess piece. But these structures aren't just beautiful, they're cosmic freezers, preserving conditions unchanged for millions of years. Inside these dark nurseries, temperatures plunge to just 10 degrees above absolute zero, cold enough to freeze molecules in place. This extreme chill does something remarkable. It slows down the chaotic dance of atoms, letting gravity work its magic undisturbed. Unlike their flashy, star-filled counterparts, dark nebulae represent star formation in its most embryonic state, quiet, slow, and hidden from view. The dust grains here act like microscopic refrigerators, radiating away any trace of heat that might disrupt the delicate collapse. What makes these shadows so valuable to astronomers is their pristine nature. While glowing nebulae are constantly reshaped by the stars within them, dark nebulae offer snapshots of star birth in its purest form. radio telescopes peer through their dusty veils, revealing intricate networks of filaments, thread-like structures where gas is quietly pooling into future stars. The Barnard 68 cloud, for instance, appears as a perfect black sphere in visible light, but infrared observations show it's a cocoon on the verge of fragmentation. The chemistry within these cold vaults is equally fascinating. Protected from harsh starlight, complex molecules form on the surfaces of dust grains like frost on a window pane. Simple ices of water and carbon monoxide coat the particles, while more exotic compounds like formaldehyde and hydrogen cyanide assemble in the darkness. Some scientists speculate that the precursors to life's building blocks, amino acids and sugars, might take shape in these frigid conditions long before stars ignite around them. Dark nebulae also solve an astronomical paradox: how the most massive stars form without blowing themselves apart. In brighter nebulae, radiation from newborn stars can halt further collapse, limiting their size. But in the depths of a dark nebula, a massive protostar can gather material in secret, shielded by its dusty shroud until it's too late to stop its own formation. Only when the star finally switches on, burning away its cradle, does the truth reveal itself: a brilliant giant born from darkness. Perhaps the most poetic aspect is their impermanence. Given enough time, even the darkest nebula will either collapse into stars or be eroded by nearby starlight. The coal sack near the Southern Cross, a pitch-black patch visible to the naked eye, is slowly being evaporated by the stars of the Crux constellation. Its fate mirrors all dark nebulae. Eventually, the shadows lift, the dust dissipates, and what was once a void becomes a beacon of light. These cosmic silhouettes remind us that creation often begins in obscurity. Before the universe lights its lamps, it works in darkness, patiently assembling the pieces of tomorrow's stars. And when those stars finally blaze to life, they carry with them the chemical legacy of their shadowy origins, proof that even the blackest patches of space are anything but empty. The moment a young star flickers to life, it doesn't just sit quietly in its cosmic cradle, it roars to existence with enough force to reshape its surroundings. Imagine a newborn star as a fiery sculptor, its intense radiation and blistering stellar winds carving into the very cloud that gave it birth. This isn't a one-way process. It's a dynamic conversation between star and nebula, a feedback loop that dictates how and how many future stars will form. The universe, it turns out, has built-in regulations to prevent interstellar clouds from turning all their gas into stars at once. Take the trapezium stars in the Orion Nebula, for example. These brilliant siblings blast their surroundings with ultraviolet light so powerful it ionizes hydrogen gas, stripping electrons from atoms and causing the nebula to glow. But that same radiation also acts like a cosmic bulldozer, pushing gas outward and creating vast cavities. Some of that displaced material collapses into new stars at the edges of these bubbles, while the rest is scattered into space, delaying future star formation. It's a self-regulating system. The more stars ignite, the more they clear out their nursery, ensuring the cloud doesn't exhaust its fuel too quickly. Stellar winds add another layer to this intricate dance. Massive stars churn out streams of charged particles traveling at millions of miles per hour, like relentless cosmic sandblasters. These winds sculpt towering pillars of gas structures like the famous pillars of creation, while simultaneously eroding them. The same forces that compress gas at a pillar's base, triggering new star formation, are also evaporating its tip. It's a race against time. Will gravity pull together a new star before radiation blows the material away? This feedback loop doesn't just shape individual nebulae, it influences entire galaxies. In regions where massive stars dominate, their combined energy can blow huge bubbles in the interstellar medium, even driving gas out of the galaxy entirely. This limits how many stars can form in a given area, preventing galaxies from burning through their fuel in a single, frenzied burst of star birth. On the other hand, in quieter corners where smaller stars prevail, gas lingers longer, allowing for slower, steadier stellar production. The Milky Way's spiral arms, with their mix of blazing giants and modest suns, reflect this delicate equilibrium. The most fascinating part, this interplay between stars and their birth clouds leaves behind cosmic fingerprints. When astronomers study the ratios of different gases in a nebula or the spacing between young stars, they're essentially reading the history of these feedback processes. Some star clusters show clear signs of having been shaped by their most massive members, while others suggest gentler, more isolated births. Even our own solar system might carry echoes of this ancient dialogue. The distribution of asteroids and comets could hint at how the sun's early winds and radiation swept through its primordial disk. Far from being passive products of their environment, stars are active participants in shaping it. They ignite, they push back, they create conditions for the next generation, or shut the door entirely. This feedback loop is why galaxies don't form all their stars at once, why nebulae have such intricate structures, and perhaps even why life had time to emerge. The universe, it seems, thrives on balance, and stars, both great and small, are its tireless custodians. Deep within interstellar clouds, an invisible tug-of-war rages, a battle between gravity's relentless pull and the chaotic churn of turbulence. Gravity, the architect of cosmic order, works patiently to gather gas and dust into dense knots, while turbulence acts like a celestial mixer, stirring the pot with supersonic motions that can tear fledgling structures apart. This delicate balance isn't just a footnote in star formation. It's the deciding factor in whether a cloud fragment becomes a star or dissolves back into the void. Picture a vast molecular cloud, its interior crisscrossed by swirling currents of gas moving faster than sound. These turbulent flows aren't random, they're fractal, cascading from large-scale eddies down to tiny ripples, like a cosmic version of whirlpools within whirlpools. When gravity tries to collapse a region, turbulence resists, injecting energy that can prevent collapse, or, paradoxically, create dense pockets where gravity gains the upper hand. It's a bit like trying to build a sandcastle in a hurricane. Some grains are blown away, while others are pressed together just tightly enough to hold their shape. Astronomers have discovered that this interplay explains why some galaxies are stellar factories, churning out stars at a furious pace, while others seem stuck in idle. In quiescent galaxies, turbulence dominates, keeping gas too agitated to form many stars. But in starburst galaxies, gravity wins, funneling material into star-forming frenzy. The Milky Way strikes a middle ground, its spiral arms acting as turbulence dampeners where gas can settle just enough to ignite new suns. The magic lies in the details. Turbulence doesn't just oppose gravity, it also creates the seeds for future stars. Shockwaves from turbulent motions can compress gas into filaments, slender cosmic rivers where material flows toward gravitational hotspots. The Taurus molecular cloud, a nearby star-forming region, showcases this beautifully. Its intricate web of filaments resembles a network of cosmic highways, funneling gas into stellar nurseries. Without turbulence, these structures wouldn't exist, and star formation might be far less efficient. Yet gravity always has the last word. Given enough time, even the most turbulent clouds succumb, their energy gradually dissipating like the fading ripples of a pond. As turbulence weakens, gravity's patience pays off, and the cloud's densest regions finally collapse. This slow victory explains why star formation isn't instantaneous but a drawn-out process, with some clouds lingering for millions of years before committing to creation. What's truly remarkable is how this balance scales across the universe. From tiny Bok globules to sprawling giant molecular clouds, the same rules apply. Even the first stars in the cosmos, born in clouds devoid of heavy elements, likely formed under this eternal dance of chaos and order. Today's telescopes are mapping these forces in action, revealing how the universe's most violent motions somehow lead to its most luminous structures. And here's the profound twist. This interplay doesn't just shape stars, it shapes their diversity. Turbulence helps determine whether a collapsing cloud fragments into many small stars or a few massive ones. It influences the spacing between sibling stars, the architecture of planetary systems, even the chemical makeup of future worlds. So when we gaze at the night sky, we're not just seeing points of light. We're witnessing the aftermath of a billion-year-old battle, where chaos and gravity together wrote the story of the cosmos. Among the countless stars birthed by interstellar clouds, a select few defy expectation's cosmic titans that blaze with the brilliance of millions of suns. These massive stars, though rare, wield outsized influence over their galactic neighborhoods, burning fiercely but fading fast. Their origins remain one of the great puzzles of astrophysics. How do clouds of gas and dust assemble such staggering concentrations of matter without the process collapsing under its own turbulence or scattering the material prematurely? The secret lies in a delicate cosmic recipe. For a star to grow beyond 8 times the mass of our Sun, it must gorge itself on gas at an astonishing rate, pulling in material faster than its own radiation can push it away. Imagine a celestial vacuum cleaner fighting against a hurricane gravity must win this tug of war decisively. Some of these behemoths, like the famed Eta Carinii, may have swallowed over 100 solar masses during their formation. Yet their nurseries are far from orderly. Observations reveal intricate networks of dense filaments funneling gas toward these growing giants, as if the cloud itself conspires to concentrate its riches in a few privileged locations. What's truly baffling is how these stars circumvent the usual limits. In smaller stars, radiation pressure halts further growth once nuclear fusion ignites, like a candle flame resisting its own wax. But massive stars seem to cheat this rule, possibly by assembling through collisions of smaller protostars in crowded cluster cores, or by forming within especially dense cocoons of dust that temporarily trap their radiation. The Pistol Star, one of the Milky Way's most luminous, suggests another clue. Its surrounding nebula shows signs of violent interactions, hinting that stellar mergers might supercharge growth under the right conditions. The impact of these giants is as dramatic as their formation. Their ultraviolet radiation ionizes vast swaths of interstellar clouds, creating glowing bubbles that can trigger or suppress neighboring star birth. When they finally explode as supernova or the even more extreme hypernova, they seed galaxies with elements crucial for planets and life: oxygen, carbon, iron. The Tarantula Nebula offers a front-row seat to this cycle, where young massive stars sculpt their environment while doomed neighbors teeter on the edge of catastrophe. Yet their rarity speaks volumes. For every star over 10 solar masses, 1,000 smaller ones like our Sun form. This cosmic imbalance suggests nature prefers building modest stars unless specific, unstable conditions align, perhaps explaining why the earliest universe lacked such giants until enough heavy elements existed to help clouds collapse efficiently. Their fleeting lives, measured in mere millions of years, make them cosmic ephemera, but their legacy echoes through the ages in the chemistry of new stars and the very structure of galaxies. Peering into the heart of an interstellar cloud with visible light is like trying to study a snowstorm through fogged-up glasses. You might catch glimpses of movement, but the true action stays hidden. That's where infrared light comes in, slicing through the cosmic dust like a warm knife through butter, revealing secrets our eyes could never see. When astronomers first pointed infrared telescopes at these murky regions, it was like flipping on a blacklight in a dark room. Suddenly, entire hidden landscapes glowed to life. Protostars still wrapped in their dusty cocoons, planetary disks taking shape, even the faint warmth of individual dust grains, all became visible for the first time. The magic lies in the physics of light itself. Those thick clouds of interstellar dust that block visible wavelengths are practically transparent to infrared. Why? Because dust grains, though tiny, are about the same size as visible light waves, scattering them effortlessly. But infrared waves are longer, sliding past the dust like a ship through gentle waves. Even more fascinating, the dust itself, chilled to hundreds of degrees below zero, emits its own faint infrared glow. This means infrared telescopes don't just see through the dust, they detect the dust's own thermal whispers, mapping its distribution and temperature with precision. Space telescopes have been the game changers here. Earth's atmosphere absorbs most infrared radiation, making ground-based observations like trying to listen to a whisper in a hurricane. That's why missions like the Spitzer Space Telescope and the James Webb Space Telescope had to operate beyond Earth's veil. JWST in particular, with its gold-coated beryllium mirrors and cryogenic chill, has unveiled details that read like a cosmic thriller, disks with spiral arms hinting at unseen planets, newborn stars firing jets of material longer than our solar system, and organic molecules coating dust grains like interstellar frost. The Orion Nebula provides a stunning case study. In visible light, it's a dazzling spectacle of glowing gas and bright young stars. But switch to infrared, and the view transforms. Dozens of previously hidden protostars appear, some still buried in thick dust pillars. One remarkable JWST image even revealed a developing star system with concentric rings of material, like a cosmic bull's-eye marking where planets might be assembling. These observations don't just add to our photo album of the cosmos. They rewrite the textbooks on how stars and planets form. Perhaps the most profound revelation is how active these seemingly quiet clouds really are. Infrared eyes have spotted protostars flickering in brightness as they binge on surrounding gas, caught dusty disks warping under the gravitational pull of newborn planets, and even detected water vapor swirling around forming stars, potential ingredients for future oceans. Every new infrared observation peels back another layer, showing us that what looks like a serene cloud to our eyes is actually a bustling stellar nursery, full of motion, change, and creation. This revolution isn't just about seeing farther, it's about seeing differently. The same patch of sky that appears barren in visible light might teem with activity in infrared, proving that the universe's most important stories often unfold in wavelengths invisible to us. As telescopes grow more sensitive, who knows what other secrets these dusty sanctuaries will surrender? One thing's certain, the infrared universe is anything but dark. It's a vibrant, dynamic realm where the future of stars, and perhaps life itself, is being woven into existence, one warm dust grain at a time. Galaxies across the universe tell wildly different stories when it comes to star formation. Some blaze with newborn stars at a dizzying pace, while others barely flicker with activity. The difference isn't random chance, it's written in the language of their interstellar clouds. Picture two galaxies side by side. One, a vibrant spiral like the Milky Way, its arms alive with glowing nebulae and young star clusters. The other, an elliptical galaxy where gas is scarce and stellar nurseries are nearly extinct. The contrast comes down to three critical factors: how much gas the clouds hold, how violently that gas churns, and whether conditions allow gravity to work its magic undisturbed. Take the Large Magellanic Cloud, our galaxy's neighbor and a stellar factory working overtime. Its interstellar clouds are packed with dense gas, some regions so rich in material they form stars 10 times faster than equivalent areas in the Milky Way. Then there are starburst galaxies like Messier 82, where entire clouds seem to collapse at once, birthing stars hundreds of times more rapidly than normal. These cosmic overachievers share a common trait: their gas reservoirs are immense, and something has shaken them up, whether a collision with another galaxy or the shockwaves from a nearby supernova. But gas alone isn't enough. Turbulence plays a paradoxical role. It can both hinder and help star birth. In quiet galaxies where gas flows smoothly, like many ellipticals, material may never clump densely enough to ignite new stars. Yet in overly turbulent environments, like those stirred by supermassive black holes, gas is too agitated to settle into stable star-forming knots. The sweet spot lies somewhere in between, where turbulence creates filaments and dense pockets but doesn't completely disrupt collapse. The Milky Way sits in this balanced state, its spiral arms gently channeling gas into productive nurseries without tearing them apart. Perhaps the most surprising regulator is something: invisible magnetic fields. Threading through interstellar clouds like cosmic stitching, these fields can prop up gas against gravity's pull, slowing star formation to a crawl. In galaxies where magnetic forces are strong, like the lenticular galaxy NGC 5866, clouds remain stubbornly diffuse, resisting collapse despite ample gas. Yet in others, weaker fields let gravity run wild, resulting in bursts of star formation so intense they can reshape an entire galaxy's structure. The ultimate control knob may be a galaxy's history. When two galaxies collide, like the famous antennae galaxies, their interstellar clouds slam together in chaotic mergers, triggering fireworks of star birth. But over time, as gas is either converted into stars or blown away by stellar winds, galaxies gradually exhaust their fuel. Elliptical galaxies, often the relics of such collisions, now drift as cosmic retirement homes. Their star-forming days long past, their remaining gas too hot and thin to collapse. What's fascinating is how these factors intertwine. A galaxy's position in a cluster, its encounters with neighbors, even the echoes of ancient supernovae all leave fingerprints on its star formation rate. By studying galaxies at different life stages, astronomers assemble a timeline of cosmic productivity, revealing why some galaxies blaze with youth while others fade into quiet old age. And hidden in these patterns might be clues to our own Milky Way's future. Will it keep forming stars steadily, or will some future collision send it into a final, fiery burst of creation? The answer is written in the clouds. Hidden in the fabric of the cosmos lies a mystery so profound it reshapes our understanding of star formation itself: dark matter. This invisible substance, outweighing ordinary matter 5-1, permeates every galaxy, including our own, weaving an unseen scaffold that holds the universe together. While interstellar clouds are built from atoms we can detect: hydrogen, helium, dust, they drift within this vast, enigmatic sea. The question isn't just whether dark matter exists, but whether its ghostly presence actively shapes the birth of stars. The idea isn't as far-fetched as it sounds. Dark matter's gravity, though imperceptible to our instruments, could act like a cosmic funnel, gently guiding gas into denser regions where stars are more likely to form. Picture an invisible hand sculpting the interstellar medium, creating subtle density variations that ordinary matter then follows. In galaxies with strong dark matter halos, like the Milky Way, This effect might explain why star formation isn't random but concentrated along spiral arms, regions where dark matter's pull could amplify the collapse of gas clouds. Yet proving this connection is like trying to catch a shadow. Dark matter doesn't emit, absorb, or reflect light, leaving astronomers to infer its influence indirectly. One clue comes from dwarf galaxies, where star formation rates often defy predictions based on visible gas alone. In places like the Draco dwarf, stars form sporadically despite ample raw material, as if an unseen force is regulating the process. Some theorists propose that local clumps of dark matter might be the hidden variable, either compressing gas to trigger star birth or disrupting it to keep the galaxy quiet. The most tantalizing hints emerge from computer simulations. When scientists model galaxy evolution with dark matter's gravitational influence included, the virtual cosmos more closely resembles what we observe. Without it, simulated galaxies struggle to retain enough gas to sustain star formation over billions of years. But with dark matter's scaffolding, gas collects more efficiently, matching the star-forming patterns we see in real galaxies. It's as if the universe's invisible architecture is quietly directing the show. Not all researchers are convinced, though. Alternative theories suggest that magnetic fields or turbulence could explain the discrepancies without invoking dark matter's role. Others argue that if dark matter were directly influencing star formation, we'd see clearer signatures in the distribution of young stars or the motions of gas clouds. So far, the evidence remains circumstantial, a puzzle with pieces that don't quite fit. The stakes for solving this mystery couldn't be higher. If dark matter does play a role in star formation, it would mean our understanding of galactic evolution is fundamentally incomplete. Entire chapters of cosmic history, how galaxies assemble, why they produce stars at different rates, even how planets like ours came to exist might need rewriting. Upcoming telescopes like the Vera C. Rubin Observatory aim to probe these questions by mapping the universe's structure in unprecedented detail, searching for the subtle fingerprints of dark matter's influence. What's certain is that the interplay between dark and ordinary matter is far more intricate than we once imagined. Whether it's shaping star-forming clouds or merely setting the stage for gravity to act, dark matter's hidden hand may be one of the universe's best-kept secrets. And as we peel back the layers of this cosmic onion, we're not just uncovering how stars are born, we're decoding the very framework of reality itself. Before the universe was filled with swirling clouds of dust and complex molecules, before galaxies took shape, there was only darkness and hydrogen. The first stars in the cosmos didn't emerge from the rich stellar nurseries we see today. They ignited in a primordial sea of pure hydrogen and helium, untouched by the heavier elements that would later become the building blocks of planets and life. These cosmic pioneers, known as Population 3 stars, were unlike anything that exists now. They were likely giants, behemoths hundreds of times more massive than our sun, burning hot, fast, and bright before vanishing in spectacular explosions that forever changed the universe. Imagine a time when the cosmos was a simpler place. No dust to shield collapsing gas, no magnetic fields to guide the flow, no previous supernova to enrich the mix. Gravity alone had to work with what little it had, pulling together sparse pockets of gas in a universe still cooling from the Big Bang. The process would have been slow at first, with gas gradually pooling in the densest regions of the early cosmic web. But once collapse began, it was unstoppable. Without heavy elements to radiate away heat, these protostars grew unchecked, accumulating staggering amounts of material before the first flicker of nuclear fusion finally ignited in their cores. The life of a Population 3 star was as brilliant as it was brief. With no elements heavier than helium to act as a thermostat, their cores reached unimaginable temperatures, burning through their fuel in just a few million years, a cosmic heartbeat compared to our Sun's 10-billion-year lifespan. Their deaths were equally dramatic. When these giants finally exploded, they didn't just fade away. They detonated as supernovae so violent they might have ripped themselves apart entirely, scattering newly forged carbon, oxygen, and iron into the void. This was the universe's first alchemy, transforming the primordial simplicity of hydrogen and helium into the seeds of everything to come. Yet for all their importance, we've never directly observed one of these ancient stars. They live on only in theory and computer simulations, their existence inferred from the chemical fingerprints they left behind. The oldest stars we can see, so-called population 2 stars, contain traces of those first heavy elements, like cosmic archaeologists uncovering fragments of a lost civilization. By studying these relics, astronomers piece together the story of how the first stars shaped the cosmos. Their explosions not only enriched the universe but also heated and ionized the surrounding gas, ending the so-called cosmic dark ages and lighting up the universe for the first time. What's truly remarkable is how modern star formation offers clues to these ancient processes. While today's interstellar clouds are far more complex, the basic physics of gravitational collapse remains the same. By observing how massive stars form, now how they gather material, how they influence their surroundings, we can glimpse how those first titans might have behaved. The key difference lies in the ingredients. Where modern stars form from material laced with heavy elements that help cool and fragment clouds, the first stars had no such luxury. Their formation was a purer, more extreme version of what we see today, uncomplicated by the universe's later complexity. The legacy of these first stars is all around us. Every atom of oxygen in our lungs, every speck of iron in our blood, was forged in the hearts of stars that lived and died long before our solar system existed. They transformed the universe from a featureless expanse into a chemical playground ripe for planets, life, and the rich galactic ecosystems we see today. So when we look up at the night sky, we're not just seeing stars, we're witnessing the descendants of those first, unimaginable giants, the pioneers that lit the way for everything that followed. Their story is our story, written in the very elements that make up our world. The universe is running out of star fuel. Right now, across the cosmos, galaxies like our Milky Way are burning through their interstellar gas reserves with no way to replenish them, a slow but inevitable cosmic energy crisis. Current estimates suggest we're living in the twilight of the universe's star-forming prime, a golden age that peaked around 10 billion years ago when galaxies were churning out stars 20 times faster than today. The evidence is written in the chemical makeup of stars. Ancient ones are metal-poor, forged from pristine gas, while younger stars like our Sun carry the heavy elements cooked up by generations of stellar ancestors. This decline isn't uniform. Some galaxies, like the massive ellipticals at the hearts of galaxy clusters, have already exhausted their gas and now drift as celestial graveyards, their stellar populations aging without renewal. Others, particularly small, irregular galaxies, still cling to reservoirs of gas and continue forming stars at a modest pace. The Milky Way sits somewhere in between a mature spiral galaxy that's converted about 90% of its available gas into stars, but still has enough left to birth new suns for billions of years. Observations of our galaxy's star-forming regions show a gradual slowdown, with current rates just 1/3 what they were 5 billion years ago. What happens when the gas runs out? The end game plays out over staggering timescales. In about 5 billion years, the Milky Way and Andromeda will collide, triggering a brief but spectacular burst of star formation as their interstellar clouds slam together. This swan song will consume much of the remaining gas, leaving the merged galaxy dubbed Milkomdo with dwindling supplies. Over the next 100 billion years, the last molecular clouds will collapse into stars, and the universe's stellar population will begin its long fade. The smallest, longest-lived stars, red dwarfs barely more massive than Jupiter, will shine for trillions of years, outliving every other object in the cosmos. Yet even in this distant era, star birth won't cease entirely. Occasionally, two brown dwarfs, failed stars too small to sustain fusion, might collide, briefly flaring into a new star. In the far future, these rare events could be the only source of fresh starlight in an otherwise darkening universe. Meanwhile, the heavy elements forged by generations of stars will become increasingly locked away in stellar remnants, white dwarfs, neutron stars, and black holes. The raw materials for planets and life will grow scarcer with each passing eon. The implications are profound. We're living during a narrow window when the universe is both old enough to have built complex elements through successive generations of stars, and young enough that fresh gas still exists to form new ones. This cosmic sweet spot may be essential for life as we know it. Too early, and planets would lack the heavy elements needed for biology. Too late, and the energy sources to sustain life would fade. As interstellar clouds thin and star formation winds down, the universe is quietly transitioning from its vibrant youth to a more subdued maturity. The age of stellar fireworks is passing, giving way to an era where the lights, one by one, begin to go out. Deep within the frigid darkness of interstellar clouds, chemistry defies expectations, transforming simple atoms into the precursors of life itself. These cosmic laboratories operate under conditions that would seem impossible for complex molecules to form. Temperatures barely above absolute zero, densities thinner than the best vacuum chambers on Earth, and bathed in harsh radiation. Yet here, amid the void, nature performs its alchemy. Water ice clings to dust grains like frost on a winter window, while more exotic molecules, methanol, formaldehyde, even amino acids assemble on these microscopic platforms. The discovery of glycine, the simplest amino acid, in comet dust and meteorites suggests these ingredients aren't just space curiosities. They might have been delivery trucks for life's starter kit. The process begins with something deceptively simple: surface chemistry in slow motion. On Earth, chemical reactions rely on heat to jostle atoms together, but in space, extreme cold becomes an unlikely ally. Atoms and molecules adrift in the cloud's tenuous gas occasionally stick to dust grains, where they linger just long enough to meet partners. Hydrogen, carbon, and oxygen atoms waltz across these icy surfaces, forming bonds that would be unstable in warmer environments. Over millennia, these chance encounters build increasingly complex structures, like a puzzle assembling itself one piece at a time in the dark. The Rosetta mission's analysis of Comet 67P revealed a stunning variety of organic compounds, including phosphorus, a key ingredient for DNA, hinting that these cosmic icebergs could have seeded young planets with life's essential elements. Radiation, typically a destroyer of molecules, plays a surprising creative role. When ultraviolet light or cosmic rays strike these icy grains, they can break apart molecules, but the fragments often recombine into more complex arrangements. It's akin to smashing Lego towers only to find the pieces spontaneously forming intricate sculptures. The Atacama Large Millimeter Array has spotted sugar molecules like glycolaldehyde in star-forming regions, while the Green Bank Telescope detected cyanothanamine, a precursor to adenine, one of DNA's nucleobases in the Taurus molecular cloud. These findings suggest that the recipes for life's molecules are written into the fabric of interstellar chemistry, waiting for the right conditions to bake them into something more. The journey from cloud to planet is anything but gentle. When a protostar ignites, its heat and radiation blast nearby icy grains, some of which clump together to form comets and asteroids. These frozen time capsules preserve the cloud's original chemistry, as demonstrated by the Murchison meteorite that fell in Australia in 1969. Inside its ancient rock, scientists found over 90 different amino acids, most not used by Earth life, proving that nature experiments with organic chemistry long before planets form. Comets like Hale-Bopp, with their tails rich in organic material, show how easily these compounds could have rained down on early Earth during the solar system's chaotic youth. What's revolutionary is realizing how universal this process might be. The same molecular clouds that birthed our Sun are still weaving their chemistry throughout the galaxy. In the Orion Nebula, the James Webb Space Telescope detected methylcation, a carbon-based molecule crucial for more complex organic chemistry in a planet-forming disk. This suggests that wherever new worlds coalesce, they're likely coated with these primordial ingredients. The implications are staggering. The raw materials for life may be as common as starlight, scattered across the cosmos by the same processes that build stars and planets. Yet mysteries remain. How did these molecules survive Earth's violent early history? Laboratory experiments show some can withstand asteroid impacts, while others might have sheltered in deep-sea hydrothermal vents. And while we've found life's building blocks in space, the leap to self-replicating systems still eludes us. That's where icy moons like Europa and Enceladus enter the story. Their subsurface oceans could be mixing these space-borne organics with liquid water and geothermal energy, recreating the conditions where life first stirred on Earth. The search for life's cosmic origins has transformed from speculation to a trail of tangible clues. Each new molecule discovered in interstellar clouds, each organic-laden comet analyzed, brings us closer to answering whether life on Earth is a singular accident or part of a grander pattern written into the laws of chemistry itself. As we peer into these stellar nurseries, we're not just studying star birth, we're tracing the lineage of every living thing on our planet and perhaps elsewhere in the universe. The next revolution in understanding interstellar clouds is already taking shape, not in the depths of space, but in laboratories and clean rooms across Earth. A new generation of telescopes, both on the ground and in orbit, stands poised to peel back the remaining mysteries of stellar nurseries with unprecedented clarity. The extremely large telescope, now under construction in Chile's Atacama Desert, will boast a mirror 39 meters across, wide enough to capture light distorted by the atmospheres of distant worlds. But for studying interstellar clouds, its true power lies in infrared vision that can peer through dust veils with 10 times the resolution of today's best instruments. Imagine mapping the magnetic fields threading through a protostellar disk or watching gas spiral into a growing star, not as blurry simulations but in sharp, dynamic detail. Equally groundbreaking are the space-based observatories joining the hunt. The Nancy Grace Roman Space Telescope, set to launch later this decade, will combine a wide field view with precision optics, allowing it to survey thousands of star-forming regions simultaneously. Unlike targeted observations of the past, this approach will reveal how factors like galactic location or neighboring supernova remnants influence cloud evolution across cosmic time. Meanwhile, ESA's Ariel mission will specialize in chemical forensics, analyzing the atmospheric composition of exoplanets to trace which molecules from their birth clouds survived to become part of their worlds. The most tantalizing possibilities come from combining these tools. Picture the ELT's razor-sharp imagery of a protoplanetary disk paired with James Webb's molecular analysis, while Roman monitors the surrounding cloud for changes over years. Such coordinated campaigns could answer long-standing puzzles. Why do some clouds form stars efficiently while others languish? How do magnetic fields guide the collapse of gas? What determines whether a cloud births solitary stars or sprawling clusters? But the real surprises may come from technologies still in development. Adaptive optics systems now being tested could cancel atmospheric distortion so completely that ground-based telescopes rival space telescopes for clarity. New spectrometer designs aim to detect vanishingly rare molecules in clouds light years away. And projects like the Square Kilometre Array Radio Telescope Network will map the hydrogen skeleton of galaxies in 3 dimensions, revealing how clouds fit into the grand architecture of the cosmos. What's truly exhilarating is how these tools will transform abstract theories into observable reality. Concepts like turbulent fragmentation, the process where gas swirls into star-forming knots, might soon be witnessed directly, not just modeled on supercomputers. The birth cries of massive stars hidden today behind thick dust could be captured in real time across multiple wavelengths. Even dark matter's subtle influence on cloud dynamics may leave detectable traces in the motions of gas filaments. This isn't just about sharper images or longer data tables. Every leap in observational power has rewritten cosmic textbooks. When Galileo first pointed his telescope at the Milky Way, he saw not a hazy band but countless stars, proving the universe extended far beyond known planets. Modern equivalents of that revelation await in the data streams of these new observatories. Perhaps we'll find evidence of star formation processes unlike anything in our galaxy, or organic molecules so complex they hint at life's cosmic ubiquity. The only certainty is that interstellar clouds, those seemingly placid veils of dust and gas, still guard secrets that will redefine our place in the universe. And the timeline, transformative discoveries could begin as early as 2028, when the ELT's giant eye opens to the sky. Within a decade, we may have answers to questions we haven't even thought to ask yet. For astronomers, it's like standing on the shore while the tide goes out, knowing immeasurable treasures lie just beyond view, and the tools to reach them are nearly in hand. While interstellar clouds appear serene in telescope images, they're actually under constant siege, bombarded by invisible bullets of energy known as cosmic rays. These aren't rays at all, but atomic nuclei accelerated to nearly the speed of light, racing through space with enough force to punch through solid rock. Some originate from our sun, but the most powerful ones come from distant supernova or even violent events around black holes. When these high-energy particles slam into a molecular cloud, they don't just pass through, they leave behind a trail of ionized gas and chemical reactions that can reshape the cloud's destiny. One of their most surprising roles is jump-starting chemistry in the coldest depths of interstellar space. In clouds where temperatures hover just above absolute zero, most molecules would struggle to form. Atoms move too slowly to overcome their natural repulsion. But when a cosmic ray strikes, it acts like a microscopic lightning bolt, ionizing atoms and giving them the energy to bond. This is how complex molecules like molecular hydrogen, the fuel for star formation, can assemble even in frigid conditions. The Herschel Space Observatory detected unexpected amounts of ionized hydrogen in dark nebulae, tracing these fingerprints back to cosmic ray impacts. Their influence doesn't stop there. By ionizing gas, cosmic rays help maintain a delicate balance between gravity and magnetic fields within clouds. ionized particles get caught in magnetic field lines, creating a kind of friction that slows gravitational collapse. This might explain why some clouds take millions of years to form stars while others fragment rapidly. In regions flooded with cosmic rays, like areas near recent supernova, the extra ionization could tip the scales, either preventing collapse or counterintuitively triggering it by enhancing turbulent motions. The famous Taurus molecular cloud shows patches of unusual star formation activity that align with maps of cosmic ray hotspots, suggesting this invisible rain might be sculpting stellar nurseries in ways we're only beginning to understand. The most extreme cosmic rays carry energies surpassing anything human-made particle accelerators can produce. Dubbed ultra-high-energy cosmic rays, these rare particles pack the punch of a fast-pitched baseball, but concentrated into a single atomic nucleus. When one of these strikes a dense cloud, it doesn't just ionize gas, it can shatter molecules, creating cascades of secondary particles that ripple through the cloud like microscopic shockwaves. Some theorists propose these events might seed tiny regions of extreme density, acting as catalysts for protostar formation. It's a controversial idea, but observations of anomalously young stars in certain cloud regions lend it credence. Tracking cosmic rays back to their sources remains one of astrophysics' great challenges. Unlike light, these charged particles zigzag through galactic magnetic fields, making their origins obscure. Projects like the Pierre Auger Observatory in Argentina use vast arrays of detectors to catch the particle showers created when cosmic rays hit Earth's atmosphere. By analyzing their composition and energy, scientists have linked some to the violent environments around supermassive black holes in active galaxies. Others might be forged in the chaotic aftermath of colliding neutron stars. Each discovery adds another piece to the puzzle of how these invisible particles shape the ecosystems where stars are born. What's truly humbling is realizing how interconnected the cosmos becomes when we account for these high-energy messengers. A single cosmic ray might travel for millions of years after being hurled into space by a dying star, only to collide with a distant molecular cloud and influence the birth of another star system. Its journey ties together events across time and space, proving that even the emptiest voids of the universe are threaded by invisible forces that might have played a role in creating the conditions for our own solar system to form. The next generation of telescopes aims to map this hidden interplay in unprecedented detail. The Cherenkov Telescope Array, with its network of gamma-ray detectors, will pinpoint cosmic ray sources by observing the high-energy light they produce. Meanwhile, radio telescopes like the Square Kilometre Array will trace how cosmic rays alter the magnetic fields within clouds. Together, they'll reveal whether these particles are mere bystanders in star formation or silent architects, subtly guiding the universe's ongoing cycle of creation. So the next time you gaze at a glowing nebula, remember, its beauty isn't just shaped by gravity and starlight. Invisible torrents of energy, older than the sun itself, are constantly rewriting its story, one atomic collision at a time. Look closely at the night sky, and you'll notice something extraordinary. Many of those twinkling lights aren't solitary suns, but pairs locked in an endless celestial waltz. Binary star systems, where two stars orbit a shared center of gravity, aren't cosmic anomalies. They're the universe's preferred way of building stars. In fact, astronomers estimate that up to half of all sun-like stars have at least one companion, with some regions like the Orion Nebula churning out binaries at an even higher rate. But how do these stellar duos emerge from the same interstellar clouds that birth single stars like our Sun? The secret lies in the physics of spinning chaos. When a dense knot within a molecular cloud begins to collapse, it rarely does so smoothly. Like an ice skater pulling in their arms, the contracting gas spins faster as it shrinks, obeying the universe's unwavering conservation of angular momentum. But there's a limit to how much spin a single protostar can handle before it becomes unstable. At a critical point, the swirling mass can fracture, splitting like a cosmic egg hatching twins. This process, known as rotational fragmentation, often creates two distinct cores that continue gathering material independently, each destined to become a star, forever bound by their shared origin. Not all binaries form this way, though. Some arise from turbulent cloud dynamics, where chaotic gas motions create multiple dense peaks within the same collapsing region. Others might result from gravitational capture, where two independently forming stars pass close enough to become entangled. But the most intriguing systems are those with extreme size mismatches, tiny red dwarfs orbiting massive blue stars, or pairs separated by distances wider than our entire solar system. These odd couples challenge our models, hinting that binary formation isn't a one-size-fits-all process but a spectrum of possibilities shaped by initial cloud conditions. The diversity of binary systems reads like a cosmic catalog of gravitational relationships. Tight binaries with stars so close they share atmospheres whirl around each other in days or even hours. Wide binaries, separated by trillions of miles, take hundreds of thousands of years to complete a single orbit. Some pairs evolve tragically. If one star swells into a red giant, it can dump material onto its companion, altering both stars' fates. Others end in spectacular collisions or supernova explosions that send the surviving partner hurtling through space like a cosmic slingshot. Studying these systems isn't just about understanding stellar mechanics, it's a window into planet formation's wildest possibilities. Planets orbiting binary stars, like the fictional Tatooine from Star Wars, must navigate complex gravitational fields. Some orbit one star, others loop around both in figure-8 paths, while unstable orbits send worlds careening into darkness. The Kepler telescope has confirmed dozens of these circumbinary planets, proving that even in chaotic systems, nature finds a way to build worlds. What's truly mesmerizing is how binary stars sculpt their surroundings. Their combined gravity can warp protoplanetary disks into bizarre shapes, funneling material into spiral arms or ejecting it entirely. In the case of massive binaries, their fierce radiation and stellar winds carve out vast cavities in interstellar clouds, influencing neighboring star formation. Even their deaths leave dramatic signatures: double supernova, binary black holes, and neutron star pairs that eventually collide, sending gravitational ripples through the fabric of spacetime. The prevalence of binaries forces us to reconsider our place in the cosmos. Our solitary sun might be the exception rather than the rule, a quiet outlier in a universe that prefers stellar companionship. As telescopes like James Webb probe younger star-forming regions, they're revealing binaries in earlier stages of development, some still shrouded in dusty cocoons, others in the throes of violent orbital adjustments. Each discovery peels back another layer of this cosmic mystery, showing us that even in the vastness of space, gravity has a way of bringing things together. Hidden within the delicate chemistry of interstellar clouds lies a cosmic time capsule, the scattered remains of stars that died violent deaths billions of years before our sun flickered to life. These ghostly signatures reveal themselves through subtle excesses of rare elements like titanium-44 and aluminum-26, radioactive isotopes forged only in the unimaginable pressures of supernova explosions. When astronomers peer into the heart of a molecular cloud like the Taurus molecular cloud, they're not just seeing raw materials for future stars, they're reading an obituary written in atomic ink, commemorating stellar giants long gone. Take the case of Iron-60, an isotope with a radioactive half-life of 2.6 million years. Its presence in modern interstellar gas is impossible unless injected by relatively recent supernova stellar explosions that occurred well after Earth's formation. In 2020, researchers discovered traces of this isotope in deep-sea sediments, suggesting our solar system plowed through a cloud laced with supernova debris within the last few million years. This interstellar visitor left behind more than just chemical clues. It may have altered Earth's climate by bombarding our atmosphere with increased cosmic rays as we pass through its remnants. The detective work gets even more fascinating when examining older clouds. Some contain puzzling overabundances of gold and platinum elements so heavy they shouldn't exist in significant quantities unless produced by the collision of neutron stars. The molecular cloud Barnard 68, for instance, shows enhanced levels of these precious metals, hinting that a catastrophic merger occurred nearby before our solar system formed. These cosmic crime scenes tell us the neighborhood where our sun was born was far more dangerous than we imagined, with violent stellar death shaping the very chemistry of our origins. Chemical forensics goes beyond simple element counting. The ratio of oxygen isotopes in different clouds acts like a cosmic barcode, revealing which generations of stars contributed to their makeup. Younger clouds near recent supernova remnants show distinct oxygen 16 to oxygen 18 ratios compared to ancient clouds in the galactic halo. By mapping these variations across the Milky Way, astronomers have reconstructed waves of star formation and death that swept through our galaxy's spiral arms over billions of years, a stellar demographic history written in atomic fractions. Perhaps most astonishing is how these echoes influence current star formation. When a supernova shockwave compresses a molecular cloud, it doesn't just trigger collapse, it seeds the next generation of stars with distinctive chemical tags. The Orion Nebula's trapezium cluster stars show unusual abundances of certain isotopes, suggesting their parent cloud was enriched by a particular supernova's ejecta. This means the stars we see today carry nuclear fusion products from stars that died when Earth's continents were still forming a celestial inheritance passed down through cosmic generations. The tools for this atomic archaeology grow more sophisticated each year. Gamma-ray telescopes like NASA Fermi detect lingering radiation from decaying titanium-44 in ancient supernova remnants, while millimeter-wave observatories pinpoint aluminum-26 concentrations in nearby clouds. Combined with supercomputer simulations of nucleosynthesis, how elements form in dying stars, we're assembling a periodic table of stellar ancestry that links the explosions of the past to the star-forming clouds of today. What emerges is a humbling realization. The calcium in our bones, the iron in our blood, even the gold in our jewelry were all created in the hearts of stars that died before Earth existed. Their final acts, cataclysmic explosions, scattered these elements into space where they became part of new clouds, new stars, and eventually new planets. When we study interstellar chemistry, we're not just examining the present, we're touching fragments of stellar ghosts whose lives made our existence possible. The universe seems to have a rulebook for star formation, but some stellar giants appear to be tearing it to shreds. Theoretical models have long suggested an upper limit to how massive a star can grow, around 100 to 150 times the mass of our Sun. The reasoning seems sound. As a star grows larger, its incredible luminosity generates intense radiation pressure, essentially pushing against the very gas that feeds it. Imagine trying to drink from a fire hose while standing in a hurricane. That's the struggle these cosmic behemoths face as their own light threatens to blow away their fuel supply. Yet nature keeps defying expectations. Stars like R136A1 in the Tarantula Nebula, weighing in at over 250 solar masses, mock these theoretical boundaries, forcing astronomers to rethink how interstellar clouds manage to nurture such monstrosities. The key may lie in the chaotic environments where these giants form. Unlike solitary stars like our Sun, the most massive stars tend to emerge in dense clusters where competition for gas is fierce. Here, the violent churn of surrounding protostars and the sheer density of material create temporary pockets where gravity can overwhelm radiation pressure, like a cosmic version of pushing through a crowd to reach a buffet. Some simulations suggest that in these extreme nurseries, multiple smaller stars might collide and merge, leapfrogging past the supposed mass limit in a single, dramatic growth spurt. The Pistol Star, another heavyweight contender, shows chemical fingerprints hinting at such a violent origin, as if it cannibalized its siblings to reach its staggering size. But even these explanations have cracks. Observations with telescopes like the Very Large Telescope in Chile reveal that some supermassive stars aren't just outliers. They're surrounded by equally massive siblings, suggesting entire batches of stars somehow sidestep the rules. One provocative theory proposes that magnetic fields, often overlooked in early models, might act like cosmic rains, channeling gas onto the star's surface in focused streams that evade radiation's pushback. Alternatively, the dust in these clouds could be clumpier than assumed, creating shadowed regions where gas collapses unnoticed until it's too late for radiation to intervene. The implications ripple across astrophysics. If stars can grow larger than we thought, their deaths become even more catastrophic. A star over 200 solar masses wouldn't just go supernova, it might undergo a pair instability explosion, obliterating itself so completely that no black hole remains. Such events could explain mysterious hypernova explosions detected in distant galaxies, whose energy dwarfs even ordinary supernova. These behemoths also churn out staggering amounts of heavy elements, potentially skewing the chemical evolution of their host galaxies. Yet for all their defiance, these giants are tragically fleeting. Stars like R136A1 burn through their fuel in just a few million years, dying young while their smaller siblings, like our Sun, settle in for billions of years of stable life. Their very existence is a high-stakes gamble, a brief, brilliant rebellion against the limits we thought governed star formation. And with every new discovery pushing the boundaries further, we're left to wonder, are we seeing the true ceiling of stellar mass, or just the edge of what our current tools can detect? The answer might lie hidden in the next generation of telescopes, waiting to reveal whether nature has even more surprises up its sleeve. Not every interstellar cloud gets to fulfill its cosmic destiny. While we marvel at the stellar nurseries that birth dazzling stars, there's a quieter, often overlooked population, the ghost clouds. These are the ones that never quite made it, dissipating back into the void without igniting a single star. Like unfinished symphonies, they leave behind faint echoes in the galactic medium, their atoms scattering to be rewritten into other stories. Yet their failure isn't truly an ending. It's a vital part of the universe's recycling program, ensuring no speck of material goes to waste. Take the faint wisps of gas drifting between the spiral arms of the Milky Way. These are the remnants of clouds that lost their battle against cosmic forces, perhaps shredded by passing stars, evaporated by radiation, or simply too sparse to overcome turbulence. Unlike the famous Orion Nebula with its glittering stellar offspring, these ghost clouds leave no visible legacy, but their fingerprints are there, hidden in the subtle chemistry of the interstellar medium. When astronomers analyze the gas in our galaxy, They find pockets with unusual ratios of helium to hydrogen or traces of rare isotopes, chemical signatures hinting at clouds that once were but never quite became. What makes these ghosts so fascinating is how they shape future star formation. When a cloud dissipates, it doesn't vanish. It enriches the surrounding space with slightly denser gas, priming the area for future collapse. Imagine pouring a cup of water into a half-full bucket. Though the cup disappears, the bucket's level rises just enough to tip the scales later. Some regions of the Milky Way, like the local bubble surrounding our solar system, are dotted with these failed clouds, their material now part of a larger reservoir that might one day coalesce into something new. The tools to study these ghosts are as delicate as their subjects. Radio telescopes tuned to specific frequencies can detect the faint emission of molecules like carbon monoxide in these diffuse regions, tracing gas too tenuous to glow visibly. The Hubble Space Telescope's ultraviolet spectrograph has caught wisps of ionized hydrogen, leftover trails from clouds eroded by starlight. Even more revealing are computer simulations, which show how turbulence and magnetic fields can tear apart a cloud before gravity can work its magic. These digital experiments reveal that for every successful stellar nursery, there might be dozens of these unseen failures, their existence just as crucial to galactic ecology as the stars themselves. Perhaps the most poetic twist is how these ghost clouds connect us to the universe's grand timeline. The oxygen we breathe, the carbon in our cells, some of those atoms likely passed through multiple failed clouds before finally finding their way into a star-forming region that succeeded. Every cosmic failure was just a stepping stone, a temporary holding pattern in matter's endless journey. So when we map these ethereal structures, we're not just cataloging interstellar casualties, we're piecing together the untold backstory of every shining star, every orbiting planet, and every living thing that owes its existence to the universe's relentless cycle of trial, error, and rebirth. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, an insatiable cosmic predator that demands constant feeding. The most voracious of these monsters power quasars, some of the brightest objects in the universe, blazing with the light of 1 trillion suns. But what fuels these behemoths? The answer lies in the same interstellar clouds that birth stars, though their journey to the galactic core is nothing short of a suicide mission. Picture a vast molecular cloud drifting through the spiral arms of a galaxy, minding its own business when subtle gravitational nudges begin altering its course. Over millions of years, these tugs from passing stars, density waves in the galactic disk, or even other clouds steer it inward. As the cloud approaches the galactic center, the black hole's gravitational grip becomes undeniable. Tidal forces stretch and compress the cloud simultaneously, warping it into bizarre, elongated shapes. The once stable cloud becomes a cosmic fire hose, funneling gas toward the event horizon in a process called accretion. What happens next defies imagination. As the cloud's material spirals inward, friction heats it to millions of degrees, creating a swirling maelstrom of plasma known as an accretion disk. This glowing donut of doom radiates across the electromagnetic spectrum, from radio waves to gamma rays. In the most extreme cases, like the quasar 3C273, the energy output is so staggering it can outshine the entire host galaxy. Magnetic fields twist this chaos into jets of particles that shoot outward at nearly light speed, spanning distances far larger than the galaxy itself. Yet the greatest mystery isn't what happens to the cloud at the end. It's how any cloud survives the journey at all. The region near a supermassive black hole is a gauntlet of destructive forces, intense radiation that should evaporate molecular gas, shockwaves from previous victims, and gravitational shear strong enough to tear apart stars. Some clouds might shield themselves with dense cores, like cosmic turtles retreating into shells. Others could be replenished by fresh gas from colliding galaxies, creating a sustainable pipeline of doom. The recent discovery of so-called G objects near our galaxy's center, strange, star-like bodies cloaked in thick gas, hints at one possible survival strategy, where clouds masquerade as stars until the last possible moment. The aftermath of this feast leaves lasting scars on the galaxy. Active galactic nuclei, powered by these feeding frenzies, can blow away surrounding gas with such force that they shut down star formation across entire regions, a process called quenching. This creates the bizarre dichotomy we see in galaxies today, some bursting with young stars, others eerily quiet, their potential for new life extinguished by their central black hole's appetites. Our Milky Way's black hole, Sagittarius A star, is relatively docile now, but evidence suggests it too had violent outbursts in the past, its last big meal leaving X-ray echoes that linger like cosmic belches. What's truly humbling is realizing how interconnected these processes are. The same clouds that nurture stars in galactic suburbs might, if nudged the wrong way, end up fueling the monster at the center. Their fate decides whether a galaxy blossoms with stars or becomes a sterile wasteland. And in that balance hangs the story of cosmic structure itself, how black holes and the clouds that feed them shape the universe, one apocalyptic meal at a time. Every atom in your body holds a cosmic secret, a journey that began long before Earth existed, in the cold embrace of an interstellar cloud. The oxygen you breathe, the iron in your blood, even the calcium in your bones were forged in the hearts of ancient stars, then scattered across space by supernova explosions. These elements drifted for eons, weaving through vast molecular clouds until gravity pulled them into the nebula that would become our solar system. You aren't just living in the universe, you are the universe, a conscious collection of stardust shaped by 13 billion years of cosmic alchemy. Think about the last time you held a glass of water. Every hydrogen atom in that water likely predates our sun, formed in the aftermath of the Big Bang itself. The oxygen, that's the legacy of a massive star that died violently, seeding its surroundings with heavy elements. Even the carbon in your DNA was crafted in the fiery core of a red giant, then ejected into space to hitchhike on interstellar winds. These atoms didn't just appear on Earth, they survived supernova, endured the chaos of protoplanetary disks, and endured billions of years of cosmic turbulence to become part of you. This connection isn't poetic metaphor, it's measurable science. Spectrometers can trace the chemical fingerprints of stars, revealing compositions eerily similar to our own bodies. The carbon-to-oxygen ratio in your cells mirrors that found in certain molecular clouds, while the gold in your jewelry shares isotopic signatures with neutron star collisions observed light years away. When astronomers study distant nebulae, they're peering into a mirror reflecting our own origins. The Horsehead Nebula isn't just a tourist attraction of the cosmos, it's a relative, a distant cousin holding the same elemental ingredients that would one day spark life. There's profound humility in realizing we're latecomers to an epoch that began before time had meaning. The nitrogen in your muscles once floated in a cloud like the Orion Nebula, cold and silent. The phosphorus in your bones may have formed in the shockwave of a dying star, then spent millions of years as ice on a comet before crashing into young Earth. Every breath you take pulls in atoms that have witnessed supernova, traveled through black hole jets, and danced in the magnetic fields of protostars. You're not just made of stardust, you're made of stories, each atom a page in the universe's autobiography. This kinship with the cosmos reshapes how we see our place in the grand scheme. The same forces that birthed galaxies' gravity, nuclear fusion, turbulence also shaped the neurons firing in your brain as you read these words. When you feel awe under a starry sky, it's more than emotion, it's cellular recognition, atoms remembering their ancient homes. The universe isn't just around us, it's within us, a living bridge between the cosmic past and the conscious present. So the next time you gaze at a nebula through a telescope, remember, you're not just observing. You're meeting the very thing that made you, a reunion 13 billion years in the making. And somewhere out there, new interstellar clouds are brewing the next generation of stars, planets, and perhaps even life, continuing the cycle that once wrote our existence into being. The universe didn't just create us, it became us, and in that truth lies the most beautiful mystery of all. From the tiniest dust grains to the grandest galactic structures, interstellar clouds are the unsung heroes of cosmic evolution. They're more than just waste stations in the void, they're dynamic, ever-changing crucibles where raw elements transform into the building blocks of everything we know. Every star that lights the night, every planet that orbits those stars, even the air in your lungs, owes its existence to these sprawling stellar nurseries. Their story isn't just about astronomy, it's about the interconnectedness of the universe itself, a tapestry woven across space and time. Consider something as simple as a snowflake falling to Earth. The water molecules in that delicate crystal once floated in an interstellar cloud, frozen to dust grains in the frigid darkness between stars. Before that, the oxygen in those molecules was forged in the heart of a massive star that died billions of years ago. That snowflake is a cosmic traveler carrying a history far older than our planet. The same is true for the device you're using to watch this video. The silicon in its circuits, the metals in its battery, all were once stardust scattered across the galaxy. What makes interstellar clouds truly extraordinary is their dual nature. They're both creators and destroyers, giving birth to stars while being torn apart by the very objects they produce. The pillars of creation in the Eagle Nebula, immortalized by Hubble, embody this paradox. Their majestic columns are simultaneously incubators for new stars and remnants of a larger cloud being evaporated by stellar radiation. This cycle of creation and destruction isn't chaos, it's a finely tuned cosmic rhythm that's been playing for 13 billion years. Our understanding of these clouds is still evolving. Every new telescope, from James Webb to the upcoming extremely large telescope, peels back another layer of mystery. Somewhere in the data streams from these instruments might be clues about how common Earth-like planets really are, or whether the chemistry of life is a universal phenomenon. The answers won't just satisfy our curiosity, they'll redefine our place in the cosmos. So the next time you step outside on a clear night, take a moment to really look at the darkness between the stars. What seems like empty space is actually a vibrant, bustling ecosystem of gas and dust, the universe's workshop. Those unlit patches aren't voids, they're canvases where the next generation of stars is already taking shape. And remember, you're not just an observer of this cosmic story, you're part of it, made from the very materials these clouds have been recycling since the dawn of time. If this journey through the dust has sparked your curiosity, don't let it end here. Hit that like button if you enjoyed the video, subscribe to join us as we explore more cosmic wonders, and drop a comment below what part of interstellar clouds fascinates you the most. The universe is full of mysteries waiting to be uncovered, and together we'll keep searching for answers. Until next time, keep looking up. The greatest stories are